Hello viewers, in today's video we are going to learn about point of zero charge. So in my previous videos you have seen that I have been talking about point of zero charge again and again. So in this video we are going to learn how to do the point of zero charge for the membrane samples. So we all know that the method used to measure point of zero charge is called salt addition, and sometimes you also call as salt titration method. And the point of zero charge is one of the key features of adsorbent, or you can say membranes, that will greatly influence the percentage of adsorption, and is different from one material to another. Okay, and this is defined as the potential or the point, usually reference to the a certain point where all the charges, okay, so you can say that total charge of an ionic compound must be zero, meaning that positive charges from cations equals the negative charges from anions. Okay, so all the charges will become neutral or zero, and below this surface is positive, above this surface becomes negative. And so if the surface is positive here, so it will attract the negative pollutants, and the surface is negative, it will attract the positive pollutant. Okay, so this decides which pollutant you are going to study for your adsorbent or for your membrane, and it controls the electrostatic interactions in adsorption and membrane process. Okay, now the methods for doing the point of zero charge or nanoparticles and adsorbents, so it is a drift method, salt addition method where we prefer to use NaCl, okay, or KCl. Okay, and there is a reason behind why do we prefer to use NaCl or KCl. They are stable, okay, and also they are neutral in nature. Then the mass titration method, the potentiometric acid base titration, the output where the pH, where delta pH is equal to 0, which is the point of zero charge. Okay, and the measurement for the membrane, so the possibility is you have to use, if the membrane is stable electrolyte, doesn't dissolve, or you can use a small punch pieces immersed in salt solution. So the dia of the, it will be around 1 centimeter square to 2 centimeter squares, and salt method is acceptable for membranes, is acceptable. If the membrane dissolves, use zeta potential instead. So if your membrane is dissolving, so you have to prefer the zeta potential, not the point of zero charge. Okay. The difference is point of zero charge tells you the intrinsic surface charge neutralization point, so which is pH dependent, and zeta potential is going to tell you the electrokinetic surface charge at slipping plane. Okay, now it also gives you the charge magnitude. Okay, and point of zero charge gives you point of zero charge, zero charge transitions, or zero potential is also defined as the effective electrostatic potential at the interface, and it can be find out by electrokinetic phenomena such as electroosmotic flow, streaming current, and streaming potential measurements, or can be calculated from the electrophoretic mobility measurements of the particles. And it is also defined as the effective electrostatic potential at the interface. Okay, now, and the values, okay, it also tells the particle stability. Okay, so your value is, if it is plus minus 30 millivolts, so it will suggest stability, while the value is less than 30 millivolt will suggest the potential aggregation or instability. So both valuable for mechanism and fouling predictions if you are doing it for the membrane. Okay, and significance in adsorption and membrane studies, it identifies the optimal pH range for polluted uptake or polluted removal, explain charge driven attraction repulsion mechanism, guides membranes fouling and anti-fouling interpretations. Okay, when the membrane will be like susceptible to fouling or anti-fouling, and it also supports reviewer comments on surface charge interactions. If you're submitting the manuscript and you're getting the comments from the reviewers, support your membrane studies, or support your effect of pH, or support your mechanical or mechanism with the point of zero charge study. So you have to do this. Okay, now the summary is, when we are trying to summarize, is simple and useful mechanism interpretations. Zeta potential components complements point of zero charge with electrokinetic data. Both should be discussed in effect of pH section for adsorption. So you can discuss both of them or either of them. For membrane, zeta potential preferred is optional but supportive. You can support. If your reviewer is asking to do the zeta potential, you can say that since most of the papers are talking about the point of zero charge for membrane also, so we are supporting, and we don't have the facility to do. Suppose you don't have the facility to do in the laboratory, you can say you don't have the facility to do the zeta potential, so you have done this point of zero charge by salt addition method. So this is all about the theoretical information, or you can say the summary of doing the point of zero charge or zeta potential. In our next consecutive videos, we will also be talking about how to do zeta potential. Hello viewers, in today's video we will find the point of zero charge. As you saw a few minutes ago, I was talking about point of zero charge, zeta potential. So now we all know what is point of zero charge, zeta potential, and why it is significant for doing the point of zero charge for adsorption studies. Okay, and why is it also significant or important for doing the zeta potential or point of zero charge for adsorption studies. And here you can see that we have sodium chloride salt. Okay, we prefer this because this is inert, it does not react. Okay, and this gives a stable reading as compared to other salts like calcium chloride, which is double charge, so there is a sharp drift in pH after doing the point of zero charge. It gives false reading. Even the sodium carbonate, that's also not preferred. Okay, so usually we prefer sodium nitrate, potassium chloride and sodium chloride. Okay, so we have now prepared 0.1 molar of NaCl by weighing around 5.84 grams in 1 liter of the distilled water. We are heating it so that the carbon dioxide gas liberates, and then what we will do, we will prepare some aliquots at different pH and then measure our adsorbent. So here the adsorbent is our different types of membrane, and usually membrane can be measured in forms of, like, if you can measure 10 grams, 10 milligrams, or you can take a piece of 1 to 2 centimeter squares of the membranes. If you see, this is the membrane, so you can take the sizes as 1 to 2 centimeter square or 10 milligrams. Okay, now let's start doing the point of zero charge for membrane. So our solution is very hot, so what I'm trying to do is to cool the solution. So I've added some water here in the beaker and trying to cool it, because this is very necessary before measuring the pH of the solution. The solution should be very cold, or it should be not very cold, it should be brought to the room temperature. Okay, so before going ahead, what we will do, we will also try to measure our adsorbent. So here the adsorbent is our membranes. Now we will weigh the membrane. So this is some membranes, so I will cut it and I will weigh it around 10 milligrams. So you can take 1 to 2 centimeter square or 10 milligrams. So this is around 10.37. We'll note down the mass. Okay, so for this membrane, which is S1, we will make 2468. So we are doing at 4 pH. Similarly, for all the membrane, we will just measure. Okay, and then we will maintain the pH and pour the solution and shake it for 24 hours. So I will skip the step. I will just measure around about 10 milligrams. Now the pH is maintained. We will pour the solution in our vials. So this is pH 2, pH 4, pH, and this is pH 6. Okay. Let us pour around 10 ml and then shake for 24 hours. Now I pour the solution. Okay. And also I will try to set the speed here, to set the speed at around 250 to 60, so that there is vigorous stirring, and then time set is 24 hours. Okay, and after 24 hours the static point will be achieved, equilibrium will be achieved, then we can check the pH of the final solution. So now we will measure the pH after 24 hours. Okay, now we will measure the pH of the solution after shaking. So this is the first one. Similarly, we will measure all the pH and note down the value and show you for all the different kind of membrane. Now this is the pH reading after shaking. Now we will plot and show you how to calculate the point of zero charge. Now we will draw the point of zero charge for the membrane, because we have already finished the running for 24 hours. So you can see that I have already copied the points. So this is my S1, S3. So we will simply just take the plot and take the line, and then we will choose line plus symbol. Okay, so after choosing this, you will get this kind of graph. So this is a graph, and you need to take some any adjustments here. So after this, you have to draw a line. So I have already drawn a line. So after drawing the line, I'll try to locate the point of zero charge. So we will choose this one. This is a screen reader. After choosing the screen reader, we'll just try to check where the line is intersecting. So there are two ways. Either you find the delta pH, subtracting the finals minus initial, or just draw the initial and final, and just draw the line from the origin where the graph are intersecting. This is your point of zero charge. So here it is 5.63. Similarly, this one is 5.72, because since the lines are very close, so either you can split the graph into two. This is 5.95, 6 point, okay, and this one is 6.30. So similarly, you can just select and then read the point, and then you can take this and then name your labels. You can do the labelings. Okay, so this is all about drawing the point of zero charge, and already we know what does a what point of zero charge means. What does it mean if it is below or above. So simultaneously we can insert these graph into the point in the effect of pH and explain the behavior of our pollutant with respect to different pH, from the extremely acidic medium to the extremely basic medium, depending on the point of zero charge what we got for the specific kind of adsorbent or the membrane